BTech in the year 2005 from JNTU Hyderabad, MTech from IIT Kharagpur in the year 2007, and PhD from IIT Hyderabad in the year 2017. Currently, he is working as an assistant professor in the Department of Computer Science and Engineering, NIT Warangal. He has 4 years of industrial experience and more than 10 years of teaching experience. His research interests are visual analytics, video content analysis, computer vision, deep learning, soft computing, and machine learning. He also published 5 book chapters, 6 papers in reputed journals, and 16 papers in conferences. He organized 4 conferences and attended 12 conferences. He is the faculty advisor for MTech students and member of Interactive Digital Board Committee 2021. He also had received Academic Excellence Award from the research work at IIT Hyderabad in 2014, 15, and 2016. He also won a first prize at IDRPT Doctoral Colloquium IDC 2016, held during 8th and 9th of December 2016. Thank you for giving me this opportunity, sir. Now I would like to hand over the session to Paul, sir.
Thanks for the kind introduction, madam. Can everybody see my screen?
Yes, sir. Visible, sir.
Yes, sir. Yes, sir. Yes, sir.
Okay, thank you. Okay. Good afternoon, everyone. As introduced, I am Dr. Ernest Paul, and I am an assistant professor in Department of Computer Science and Engineering at NIT Warangal. So in today's session, I am going to discuss about how deep learning can be used for video analytics. So why deep learning? So before we enter into these applications of deep learning, let's see the traditional machine learning workflow. So in the traditional machine learning workflow, given a data, so here we are trying to classify if the given input image consists of cars or not. So given this problem, the given input image is given as input for feature extraction. So feature extraction, a domain expert identifies what features can be used for the given recognition task. So these extracted identified features will be given as input to a classification model, and the output of the classification will be the label whether it is car or not a car. So this is the traditional machine learning workflow where the feature extraction step is the crucial step. The reason being that the features are the representation of the input data. If the features are not effective, the classification model won't be able to discriminate them. So this is the reason why the traditional machine learning workflows, they are dependent on these handcrafted features. So when you need to apply this approach to another task, we need to change, in most cases, the features that are used, thereby the entire approach, okay, the performance of the approach significantly differs from the original approach. But with the introduction of deep learning, as you can see in this pipeline, so both the feature extraction and classification, both tasks are done by the neural network. So here you can see a neural network, and this neural network, this is the input layer, this is the output layer, and there is one hidden layer. In this neural network, there are 2 hidden layers. So a deep neural network is generally used to implement the deep learning models. And this particular one is referred to as a DNN based classifier. So here the last layers contain the classification, the functionality for doing the classification. So this is the deep learning workflow where the raw input image is given as input to the deep learning model, so that directly the classification can be done. So this workflow is the traditional pure deep learning approach. And there are some factors that you need to take into consideration when using deep learning. So this computation, the deep neural network implementation, it is strongly recommended to use parallel computing resources like GPUs. You need large volume of label data because you are trying to learn the necessary discriminative features from the raw data. So these are the main concerns when you are planning to use a deep learning approach compared to a traditional machine learning approach. Is there any question?
No, sir. Sorry, sir. I muted all.
Okay.
You proceed, sir.
Okay. Thank you. So here, as mentioned on the left hand side, you can see that we need a domain expert to work on a particular domain if it is the traditional machine learning approach, because the domain expert identifies the necessary discriminative features. But with the deep learning approaches, you don't need a domain expert because the necessary discriminative features are automatically learned from the raw data. So this is the main advantage of deep learning models. Basically, you don't explicitly need to specify what features needs to be extracted. The model itself will identify what are the best discriminative features for the given data. So deep learning models learns multiple levels of representation or abstraction. So on the right hand side, you see a figure. So digital image consists of pixels. Pixel is the smallest divisible picture element. It is shortened for picture element, and it is the smallest visual element. So here the pixel based image is given as input to the deep learning model. And in the first stage, we will learn the edges. And the group of edges are used to learn the parts of the objects, and these parts of the objects are used to learn the object models. So here, as you can see, this is multiple levels of abstraction, and the higher level concepts are described from lower level concepts. Generally, it is applied for image data, audio data, and textual data, but nowadays it is applied for other modalities as well. These deep learning models are generally implemented using artificial neural network, and some of the most popular deep learning models are CNNs. So there are various design principles for each of these deep learning models. For convolution neural network, these are the design principles. There are other design principles in the recent literature like Dropout and others, but these are the design principles for the traditional CNN architecture, which are local receptive field, weight sharing, and spatial and/or temporal subset. We will look at these design principles, as well as in addition to CNN, I am also going to discuss the working of a stacked autoencoder, so that we have two models to compare how these different deep learning models work. So this convolution neural network, it is a variation of this multi-layered neural network. And it also learns hierarchy of features from input data. And it is trained using a variation of backpropagation algorithm. So far, we have seen these neural networks represented in linear order, linear fashion. But when we are dealing with image data, it is two-dimensional data where there is a correlation between the X and Y pixels. So that is the reason why the neurons in a convolution neural network, okay, internally they will be arranged in this fashion. So basically this is the logical arrangement where this neuron is taking input from these 9 neurons which are arranged in 3x3 fashion. Similarly, here also we are selecting input from 3x3 and so on. And finally, if you see here, this is the classification part. Here we will see a fully connected neural network. This is used as a classifier, and the first part acts as the feature extractor. And these are the given the images of faces. These are the parts. These are the edges, these are the parts, and these are the objects that are automatically learned from the data. So given a deep learning model that is trained for recognizing faces, I can use the same model for recognizing cars by training the model on car data. I don't need to change the architecture at all. I just need to train it for images of cars, and I'll be able to use it for recognizing cars. Similarly, I can use the same model for recognizing elephants and chairs also, one at a time. So here, the main advantage of deep learning models is with minimum or no changes, okay, we can apply the model trained for one computer vision task to a similar computer vision task with minimum or no changes. So here, for this particular case, so this is a binary classification for faces. If it is cars or elephants or chairs, okay, there is no change in the architecture. But let's say I want to support multiple classes. If I want to classify the input image into one of these 4 classes, then all we need to do is increase the number of neurons in the output layer and add connections to the previous layers. So that is the reason why the main advantage of deep learning models is with minimum or no changes, we can apply a model trained on one computer vision task to a similar computer vision task. So there are primarily 3 ways a convolution neural network can be used. The first one is you need to define from the scratch. You define the architecture from the scratch and train it on raw data. Okay. So here the problem is that you need to explore the architectures a lot, as well as you need large volumes of data. Okay. The reason being that you are training the entire architecture from the scratch. The second way is use a pre-trained model for feature extraction. If you are using a pre-trained model for feature extraction, you are using a existing architecture. So you don't need to train it. Okay, you just need to use the existing architecture. And the data also, because you are using the pre-trained model for feature extraction without training the model, okay, you are only training the classifier, okay, on the extracted feature. So here, moderate or less data is also fine. Then the third case is transfer learning. So in transfer learning, you use a pre-trained architecture. Okay. Then you will train, you will freeze the initial layers and you will train the weights of the layers in the second half. Okay. So as a result, you don't need to explore a lot of architectures. Basically, as the name suggests, transfer learning, you are using the weights that were learned in one domain and trying to apply it for the other domain. So here also, you don't need the large volume of data. Moderated data is fine. So these are the 3 approaches. So unless you are using the first case where you are training from the scratch, then you need to explore a large different possible architectures and train them from the scratch. This is time consuming as well as it requires a lot of empirical study. The second case, in case of using a pre-trained architecture for feature extraction, you are using a pre-trained architecture and you are only training the classifier. So as a result, you don't need a large volume of data. And in the final case, the transfer learning, you are using a pre-trained architecture and adjusting the weights in the final layers so that it is optimized for the given task. So here also you don't need large volumes of data. So these are the three ways in which these DNN models, especially the CNN model, can be used for a given computer vision task. Now let's discuss convolution neural networks. So convolution neural networks, as the name suggests, you have the convolution operation as well as the neural networks. So a convolution neural network has this convolution operation. In convolution operation, we consider two images. One we consider as the input image and the other we consider it as the kernel matrix. So here, the convolution operation involves taking this kernel, flipping it horizontally and vertically, and applying this filter on the original image. So basically, this will be a 3x3 filter. As you can see, this is of odd size. Generally, we take odd size filters because the center, okay, it is overlaps with a pixel. So this one, we place this filter at this location. We computed the dot product, and this dot product value is substituted. This is the output matrix. Then we slide it by one step, repeat the process. We slide it by one more step, and we repeat the process, and we compute this value. So once this one row is done, we will slide it vertically by one step, compute the value, and repeat the process until the filter moves across all the locations in the image. So this is the convolution operation, and in traditional image processing, depending upon the weight values that are taken in the kernel, different outputs are produced. For example, if I take an averaging filter, it creates blurring effect. If I take edge detection filters like Prewitt-Sobel operators, it will compute the edges. So in convolution neural network, we learn these kernels which act as the feature detectors. So that's the how this convolution operation is related to a convolution neural network. We'll see how this convolution operation can be implemented using a neural network also in a minute. So this is how the traditional these weights have effect on the output. So now, how do we implement the convolution using a neural network in a convolution neural network? So here, let's consider 8x1. Instead of using 2D image as input, I'm considering linear for the sake of illustration. So if 8x1 input and 3x1 is the filter, then I place this filter overlapping these cells, and the value of the convolution is computed here. Then I slide this by one step, compute it here, slide it by one more step, and so on. Finally, the filter will be located at this point. So this is how we do the convolution operation of this 3x1 filter on this 8x1 image. So as a result, this 6x1 output will be produced. So here, if you see, in a traditional neural network, in a fully connected neural network, a neuron will take input from the output of all the neurons in the previous slide. But in this case, if you see, if I consider each cell in this column as a neuron, this is taking input from only 3 neurons in the previous slide. So this is the idea of local receptor field. And the other point is, if you see the number of distinct weights between these two layers. So even though there are multiple connections, the number of distinct weights correspond to these 3 colors. Okay, so basically, This is the concept of weight sharing. Due to weight sharing, the number of distinct variables that needs to be learned or minimized to the number of weight values in this kernel. Then the concept of subsampling. So here we are looking at this spatial subsampling. So given this 8x1 input, assume that I'm using this 2x1 filter. So I place this filter at this location. Let's say I'm doing max pooling. The maximum of these two will be placed here. Similarly, non-overlapping locations. And these are the other locations. So like this 4x1 output is produced from 8x1 input after applying this 2x1 filter. So this is a subsampling, which is the third principle. So basically local receptive field, weight sharing, and subsampling. These are the three principles for the design of a convolution neural network in the classical CNN. Let's see the illustration when we are using this 2x for image data. So if I'm considering this 5x5 convolution, I slide this filter on the input image and these output values that are generated, I refer to them as feature map. Since the kernel is run within the image, I'll get an image which is slightly less than the input image. Then considering a subsampling layer 2x2, I'll place the filter at non-overlap value and repeat the process for all the locations. So in the animation, I'm only showing partial image, but on the entire image, this operation is done. And the output, we are considering it as a feature map. So here, as I'm using 2x2 subsampling, the size reduces by half. And I repeat the process by considering alternative convolution and subsampling. Thereby, I get a 1x1 output. So this feature that are extracted by CNN are referred to as the ConNet features. So basically, ConNet is shortened for convolution neural network. So ConNet features are effective for various visual recognition tasks. So here, this is an illustration of 2D convolution where this is the filter applied on this image and the output at this corresponding central location, it will be computed. In a 3D convolution, we have filters across multiple planes. So here, this is black, the middle one is red, the front one is blue. So when I apply this, so basically a video is a sequence of images. So you can consider them as time 0, 1, 2, 3, and so on. Okay. So here, when I apply this 3D convolution at this location, so it overlaps with the central, let's say this is A, B, and C. So A overlaps with this one, this is B, and this is C. Then when I slide it by one step, so A overlaps here, B overlaps here, C overlaps here. So like that, the 3D convolution operation can be used for capturing the patterns, spatio-temporal patterns. So basically using 2D convolution, we can capture spatial patterns. Using 3D convolution, we can use for capturing spatio-temporal patterns. So here, this architecture is one of the first architecture used with a 3D convolution for human action recognition. And as I mentioned, this last couple of layers corresponds to the classification task. So why ConNet features are effective? To explain that, we will see an illustration of LeNet 5 by Jan LeCun. So our The information is available here. So this is for MNIST handwritten digit recognition task. As you can see, this is the input and this is the predicted label. And these are the intermediate results. So here, even if the input is shifted, rotated, or there is a change in scale or change in width of the pattern, or even if the input is stretched or squeezed, okay, we can see that the model is able to predict accurately. Now, if you see at the second part, even if the input is partial patterns, if there is random noise, or if there are overlapping patterns, even under all these cases, we are able to recognize it correctly in most of the cases. So this is the reason why we say that ConNet features are robust to variation in input representation and noise. So now let's look at the stacked autoencoder, which is another deep learning model. So to explain this, I'm going to consider this architecture. So this stacked autoencoder is trained using greedy layer-wise training principle. To explain this, I'm going to consider this architecture where there is one hidden layer, second hidden layer, this is the input layer, and this is the output layer. So in a stacked autoencoder, we use an autoencoder, which is a neural network which tries to produce the output same as the input. So here, this is input is of dimension 6. The output is also dimension 6. So basically, we are trying to find an encoder, okay, which finds a lower dimension representation of the input data, and we decode it back to dimension 6. So this is an autoencoder. Once this encoder is trained, I'm going to take the activations from this hidden layer, referred to as feature 1, and train another autoencoder using this feature 1 as input, so that I can find another encoder and decoder which finds a lower dimension representation of this data. So once I train this second autoencoder also, I'm going to extract the features of this hidden layer and then going to train a softmax classifier. So the softmax classifier input is the features 2, and the softmax classifier, the output is the probability that the input belong to each of these particular classes. The sum of all these probabilities will be equal to 1. So once this softmax classifier is also trained, I'm going to stack these individual layers. So basically, I will learn the encoder 1, then I will learn the encoder 2, then I will train the softmax classifier, then I'll give the input to the first encoder and take the output from the softmax classifier. Okay. So this, if you see, it looks like a stack of these various layers that were trained independently. So that is why we say that this approach is based on the greedy layer-wise training, and it is named as stacked autoencoder. Here, autoencoder is used to learn these encoding layers, and this stacking concept related to stacking is used to build this stacked autoencoder. So this is the entire approach, and what we generally do is, once we build this stacked autoencoder, we train it using backpropagation algorithm to optimize the weights. Thereby, it will improve the performance. If I need to implement this in a programming language, let me show the demonstration in MATLAB. So this is the code for implementing the stacked autoencoder. So the first step is loading the data. So this is the NIST handwritten digit data. So that's why it is 28 cross 28. Then we are going to train the first autoencoder. So here 28 cross 28, it is the input dimension is around 700. Then I'm going to train the first autoencoder with 100 number of neurons in the hidden layer. So once the autoencoder is trained, I'm going to extract feature 1 from this first autoencoder. Then I'm going to train a second autoencoder using feature 1 as input, considering 50 neurons as the number of neurons in the hidden layer. Once the second autoencoder is also trained, I'm going to extract feature 2 from this autoencoder. Then train a softmax classifier using this feature. So once this is also trained, I'm going to stack the encoder 1, encoder 2, and the softmax layer to build the stacked autoencoder. So once this stacked autoencoder is built, I'm going to compute the performance and plot the confusion matrix. Then I'm going to train using the backpropagation algorithm to optimize the performance. Then again, I'm going to compute the performance and plot the confusion matrix. So let me run this. So this is a CPU only code. So that's why when during the execution, the CPU utilization will reach around 100%, especially the first autoencoder. You can see that the CPU utilization is almost 100. So this is the reason why the parallel computing resources like GPU is strongly recommended. The reason being that due to parallel computation with the GPU, you will be able to complete this process, especially the training takes longer time. The training can be done faster if you have a GPU. So once the first autoencoder is trained, we are going to train the second autoencoder. This is going to be faster than the softmax layer. Then the optimization. So now let me explain the various results in detail. So this is the first autoencoder that was trained. So 28 cross 28 is 784. So 784 to 100, again back to 784. This is the first autoencoder. So this is the second autoencoder, which is taking input of dimension 100, reducing it to 50, and again decoding it to 100. This is the softmax classifier. So input dimension is 50, output dimension is 10. Then when we combine these three, we will get a stacked autoencoder. Input is 784. After the first layer, dimension is 100. After the second layer, dimension is 50. The output is of dimension 10. So this is the confusion matrix associated with the stacked autoencoder as soon as it is built. And on the right hand side is the confusion matrix after fine tuning. So on the left hand side, if you notice, okay, there are around 500 observations in each class. You can see that in some of the cases around 200 observations, and in this case it's only 167 observations were correctly classified. So basically the diagonal elements represent the correct prediction, non-diagonal misclassification. So here the overall accuracy is around 57% only. But on the right hand side, this confusion matrix corresponds to the model obtained by training the initial model using backpropagation. So here you can see that more than 480 observations are correctly classified for all the classes. So here you will get an accuracy around 98.2. So here we can conclude that, okay, after obtaining that stacked autoencoder, if we train it using the traditional approaches, we will be able to optimize the weights for better performance. So this is the working of a stacked autoencoder and the demo of the stacked autoencoder. Any doubts in the stacked autoencoder?
Yeah, Professor Paul Bhanumurthy from VVIT.
Sorry, sir.
Bhanumurthy from VVIT. Hello, can you
Yes.
hear me?
Yes, sir.
Yeah, I'm Bhanumurthy from VVIT, Dept of ECE.
Yes, sir.
So yeah, it was a very insightful presentation, Professor Paul. So can this stacked autoencoders that pre-train as CNN can perform tasks beyond image recognition, like NLP or time series forecasting?
I believe there are approaches related to that, sir, but it's not covered in this presentation. There are
Okay, yeah.
in the literature, there are approaches for that.
Okay, okay. Right. So beyond image recognition, stacked autoencoders can pre-train a CNN.
Stacked autoencoder and CNN are different approaches, sir.
No, stacked encoders, they are pre-training a CNN, right? They are used to pre-train a CNN.
No, sir. Stacked autoencoder is different. CNN is different.
Okay.
These two models, I've just shown it for how they will be used for classification. In my next presentation, I will discuss 4 case studies. In one of the case study, I'll show how these two models can be used for image classification.
Okay. So stacked encoders are not implemented to pre-train a CNN. So these two are different.
These two are different.
Okay, thank you.
Okay, sir. Okay, then I'll continue with my presentation. So this is just a visualization of the pre-trained models. Now coming to video analytics. So human behavior analysis. So the human behavior analysis, there are various terms. So in this presentation, I'm going to consider this terminology proposed in this paper, where a motion involves atomic movements of limbs. Actions or events, it is a sequence of motions or gestures. These actions or events happen for a duration of few seconds to minutes. Then activities, which is a sequence of actions, they last for few minutes to hours. Then the behavior, for example, human behavior, once we observe the activities of a person over duration of hours to days, we will be able to infer the behavior of a person. For example, let's say the take the activity of cooking. Okay. So cooking involves, let's say, the events of cleaning the vegetables, cutting, cooking, and serving. And let's say the event of cutting involves the periodic motion of knife on the vegetables. So like that, once we accomplish this sequence of motions, we will be able to accomplish this activity, or sorry, be able to accomplish this action, and this sequence of actions will accomplish the activity of cooking. And for example, behavior, we say that somebody is a kind person, gentle person, or rude person based on their behavior, okay, observed for few hours to days. So this is the terminology that is proposed in this literature, and in the literature sometimes they are used interchangeably also. So to identify this behavior, these are the common modalities that are used. So basically, from the motion of the subject of interest, the objects with which the interaction is happening, the audio patterns associated with the action, as well as the environment in which the action is being performed. For example, somebody is crying. If somebody is crying, without the audio information, to recognize that somebody is crying, it is very difficult. For example, we can use the facial expressions, but we need to capture the expressions from the front side. So we need to get the front face with the expressions clearly, or we need to recognize tears. Okay. So both these actions are much challenging to accomplish compared to using the audio patterns to recognize that event. Similarly, for various cases, some modalities will be more effective than the others. And there are actions associated with single person, interaction, it is a group, or it is a crowd behavior. So what is action recognition? So action recognition aims to identify the goals of one or more agents from a sequence of observations of agents' movements in an environment. For example, this is interaction. So interaction, it is between two people. And you can notice that, okay, ideally the interaction should be captured in this direction. If you capture it from behind one of these persons or from the top side, it won't be effective in recognizing these interactions. Then this is the first motion picture. Here we mentioned the sequence of observations. So this first motion picture is obtained by placing the cameras on a racetrack, and as a horse is passing by, photograph is taken, and if you show those images in sequence, you will get this motion picture. So the sequence of observations are needed to capture the motion information. And the last one is, I assume you're all familiar with yoga. Okay. So this is referred to as surf yoga. So here, as you can guess, the yoga is done on a surfboard. And this is a special case where yoga is performed on the surfboard. Okay. So there are many such actions, events, activities which are variations or extensions to the basic versions of these particular actions. So that is why it is very challenging to recognize the actions in the real world. The reason being that you cannot restrict the angle or the direction from which you are taking these observations. It might change and it might not be optimal direction. So this is an example of the observations. So here you can see this is a video from a data set. Can anybody identify what's happening in this video, the first video? Any guesses? So here, this is the answer. Okay, so this is a video from this snatch data set. So what's happening in this video is this biker, okay, he is coming beside the auto, snatching the chain and leaving. So unless this is the region of interest, and in real world it is very difficult to capture or recognize such kind of actions due to the diversity of the data. And the second case is in a handheld camera. You can see this UC50 data set. This is a mounted camera due to which there is no camera motion. The second case is a handheld camera where there is a slight motion. And in the third case, it is an aerial camera. You can see a lot of motion. So due to which, depending upon the data, what other factors that you need to consider, take into consideration will also change. And there are multimodal data sets also where you have color information, the depth information, and infrared video. Depending upon the modalities, they have their own advantages and disadvantages. So these are some of the applications of this human action recognition. So around 500, more than 500 hours of video is being uploaded into this YouTube and other websites. So this data needs to be organized and categorized effectively for the video content analysis is essential. So to categorize the movies, okay, one can identify the various actions that are happening, and depending upon the frequency of these actions, we can categorize the movies into various genres. Similarly, for sports analytics, we can identify their motion and then advise the optimal training regime. So like that, video content analysis, okay, is essential for many of these human-centric actions. So basically, this video content analysis, it is human-centric. That's why human behavior analysis, majority of the videos, we collect the videos of humans, and we do the analysis also based on what the human is doing. So that is why the human-centric analysis is, okay, the primary area of study when we are working on the video analytics. So this is another set of videos, the applications. So for fire detection, this is also another video from chain snatching. This is from road accident detection, and this is signal violation, and this is helmet detection, and this is a case of elderly fault detection. So these are all applications of visual analytics. So these are the case studies that we will discuss in this today's session. So the first one is how motion capture information can be used for action recognition using CNN and stack dot encoder. The second one is an ensemble based approach for recognizing human action. The third one is the hybrid deep learning model using genetic algorithm to train a convolutional neural network. And final study is how multimodal information can be used for human action recognition. So this is the first approach. So mocap information. So mocap stands for motion capture. There are markers that will be placed on this subject, and based on the location and the tracking information of these markers is used to recognize the human actions. So this is a video from the Berkeley MHAD dataset. So here, these are various observations of the same action. So you can see different subjects wearing the same specialized dress with these visual markers, and these actions are performed in a special environment where their motion is captured from various angles using multiple cameras. As a result, there won't be any issues related to appearance and capturing conditions. The only factors that we need to address are different subjects will have different physical characteristics. The observations across repetitions, they might not be identical. And across different subjects, there will be slight variations. So these are the factors that we need to address when we are considering motion capture information for action recognition. So this is the overall architecture. So basically, this is the motion capture information. So the black dots corresponds to the visual markers, and this, when they are connected, we can get the skeletal information. From this skeletal information, so this animation is for the action of sitting and standing. And in the middle, you see these various joints. And from these, I'll find some distances, and this distance information will be processed using these fuzzy membership function, which are like transfer functions, to enhance the discriminative information. This representation, when I concatenate them, I'll be able to get an image representation, which will be used as input to these deep learning models for recognizing the actions. So these are the various markers. This is the skeletal information. The one that we are considering are marked in red. So here you can see that the hands, the pelvis, and the feet. So these are the points that we are considering among all the available information. So this hands, the pelvis. So from these, I am computing 4 distances, which are the distance between the hands, height of the hands, and height of the pelvis. So using this information, I am going to recognize some of the human actions. Actually, these distances are dependent on the characteristics of the person who is doing the action. So that's why we need to normalize this information. To normalize this, I consider this pose, which looks like a T pose. So using the T pose, I'll be able to find the physical characteristics like height of the person, length of the hand, and so on. The subject is made to do this T pose before performing the actions. So using this T pose information, I'm going to normalize these distances computed between these markers. And then I'm going to use it for recognizing the human actions. So the first study we are performing on CMU mocap dataset for locomotion actions. So locomotion actions are jump, run, and walk. So these are the main actions, but there are 27 subcategories and 201 observations associated with these actions. So here I am considering the one-shot training. So where I am considering only one observation to train the approach. So these are the actions that are considered in this study. So when I plot this jump action, so here the height of the feet above the ground, let's say P and Q are the height of the left foot and right foot above the ground. I am normalizing this information considering the maximum value of that variable in the observation. So using this function, I am normalizing it so that it varies between 0 and 1. And as you can see, when it is jumping action, both of them are varying simultaneously. In a run action, they are varying alternatively. In a walk action, with some delay, they are varying alternatively. So here, what I'll do is, I'll take multiple samples using something like a sliding window, and use these samples to train the model. So these are the samples that are obtained using this sliding window on this single observation, and from these I'm going to get the use it for training. So here, from this information, how did we get this image? To understand that, so to plot the variable p, it is varying from 0 to 1. So this is the variation of p. I put a blank line, then variation of p, it is varying from 0 to 1. I'll scale it to vary from 0 to 255, which is the intensity variation of grayscale image. Then I put a black line again, I'll put a Q, then this is again black. So that is why this is like P and this is like Q. So here, this is the image representation obtained from this variation of this P and Q variables using this mechanism. So this images are used to train the model, and once it is trained, I'm going to use it to test on the remaining observations. So this is the another data set, which is the Berkeley MHAT data set. So this is the subject. You can see the various visual markers, and this is the depth information, and this is the sensory arrangement, and this is the statistics of the various observations. So these are the 11 actions in this data set. As you can see, the blue color corresponds to the front view, the red color corresponds to the side view. And there are actions like sitting and standing, in which, if you notice, the height of the pelvis above the ground. So the height of the pelvis above the ground, it will change to a value lesser than the normal value in case of sitting and standing actions. So this is the normal value. When they sit, it reduces to a lower value. And in case of jump and jumping jack, it increases to a higher value from the normal value. Actually, it increases and decreases. So it's like, so here this is the normal value, this is lower, and this is higher. So it is like a varying sinusoidal. And for the other actions, the height of the pelvis above the ground is almost constant. So here, the domain knowledge about the movements involved in the action is used to identify these distances. Why did we consider pelvis? The reason is, due to the nature and range of variation of this variable, I'll be able to distinguish these actions from the rest of the actions. Similarly, for clapping action, I'll use the distance between the hands. And for waving one hand, waving two hands, and let's say bending. Okay. For these kind of actions, the height of the hands above the ground. So if you see here in bending action, they have the highest value as well as they have the least value. And in waving one hand and two hand, okay, it will be like in a sinusoidal variation. So this domain knowledge is used to identify these distances. And if we do further analysis, so this is the variation of these variables. So D is the pelvis. So here, as I told you, the height of the pelvis above the ground will be smaller, will be less than 0. This is the normalized distance. So this will be less than 0 in case of sitting and standing related actions, and in jumping related actions, it will vary like in a sinusoidal way. And for the other actions, it will be almost constant at 0. And if you see B and C, which are the heights of the hands above the ground, you can see that they are varying simultaneously in waving two hand, and in waving one hand, only one is varying. In bending, they are varying simultaneously. So using this information, okay, we do further analysis. For example, the distance between the hands. If I plot the distance between the hands, for example, let's say this is the variation in one of the observation and this is the variation in another observation. I'm considering the only variable A, and for multiple observations of the same action, I find the range of variation of maximum value as well as the range of variation of minimum value. So the maximum value is shown in red, the minimum value is shown in blue. If I plot those values, the range of variation for each of the action for this variable A, you can notice that for clapping related actions, it is having a range smaller than all the other actions. That's why I've taken this threshold and I've used this normalization function. So this function is equivalent to this equation. So this fuzzy membership function, it is like a transfer function, a compact way to represent the transfer function. So using this function, I'm going to emphasize this discriminating information so that if you see this clapping related action, I get a typical representation like this. Similarly, for height of the right hand. So here, if you notice, when we are doing the bending action, the smaller range, the least value, it will be at a different range compared to the rest of the actions. Similarly, for waving one hand and two hand, it will have a range higher than the rest of the actions. So that is why I've taken a threshold here, and in the negative axis, this is the transfer function that I am using to emphasize this information. Similarly, I am taking this transfer function to emphasize this discriminative information. So here you can see this is the typical representation for bending related actions, and this is the typical representation for waving one hand. So this is for the right hand. I'll do something similar as F3 for the left hand also. As a result, the same function is used for the left hand also. Then we have the height of the pelvis above the ground. So this is where you can clearly see that for bending related actions, the minimum range is at a completely different range compared to the rest of the actions. So that is why I take a threshold here, and in the negative axis, if it is less than this, then I'm going to use this. So here this transfer function is used to emphasize this discriminative information. Similarly, for jump and jumping jack, you can see that the height of the pelvis above the ground will be greater than 0.05. So that's why I use this transfer function to emphasize this discriminative information. So as a result, we have 6 functions. So when we put these things together using this representation, I get this typical representation for these 11 actions. So we have similar representation for CMU actions as well. So now that I got image representation for this mocap related actions, I can now give these images as input to deep learning models. So these are the 2 architectures that we have used. So first is the CNN and the next is stacked autoencoder. So with CNN, we are able to get 97 and stacked autoencoder 98 for this Berkeley MH80, and on the right hand side we see the confusion matrix. Similarly for CMU mocap dataset, stacked autoencoder got slightly better results than CNN. The reason could be that the CNN is learning local patterns, but stacked autoencoder is learning the global patterns. The confusion matrix is shown on the right hand side. For example, these are the features that are learned by the stacked autoencoder for these 2 data sets. For example, if I consider a local pattern, so using these 2 local patterns, I won't be able to distinguish which action it is. So this could be the reason why stacked autoencode might be doing slightly better than CNN. For example, if you see these jump actions, okay, you can see many of these with a pattern similar to this jumping action. So this could be the reason why stacked autoencoder was able to perform slightly better than CNN in this particular case. Now coming to the second approach, where we are going to design a hybrid deep learning model. Basically, it is an ensemble model where we are going to use it for human action recognition. So for this, we consider this action bank representation, where an action bank is a set of videos which contains multiple examples of the same video captured in different conditions or characteristics. So given a video, the similarity of that video with these templates is computed. So these are 3 videos of boxing action, and let's say there are n templates in the action bank. The number of rows will be equal to n. So each row, the output of each row, each row corresponds to the output of the similarity of the video with a template video. So here you can see that at this particular location, for all these actions, there is a high similarity. The reason could be that the template associated with this row is for boxing action. That is why for all the boxing videos, we are able to get high similarity. Similarly, for other rows with a high similarity. So here we can observe that if we can identify the rows associated with each action, we will be able to recognize the actions from this action bank representation of videos. So using this principle, what we have done is we have tried to develop a CNN architecture which preserves the number of rows. So here is the number of rows. The number of columns is 72. We are considering only linear filters in convolution and subsampling. As a result, we are preserving the number of rows, and this information is given as input to a fully connected neural network for classification. So when we have done this study for 5-fold cross-validation on UCF 50 data set, we are able to achieve an accuracy of around 93%. So here the idea is to design a fusion model, okay, in which so this is a Venn diagram. Let's say this is the universe of observations that we are testing, and let's say these are 2 models. So the circle represents the number of observations correctly classified by model A, and similarly correctly classified by model B. So here the idea of fusion approach is we are trying to find A union B. So A union B will be greater than, okay, A and B if there are observations correctly classified by only one model. So here this A intersection B is 0. Okay, so this is the case where A union B will be maximum. So when we are computing A union B, for example, if I take an observation here. So here what should be the case is let's say this is the prediction of A and this is the prediction of B. Okay. So with, let's say, 0.8% confidence, we are able to predict it incorrectly, and B is able to incorrectly predict with a confidence of 0.2. So if that is the case, when we are combining the performance of these 2 models, we can use the confidence information. Whichever has a higher confidence, I take that as the confidence value of the combined model, and similarly that label. So as a result, what will happen is we will select the prediction with higher confidence. As a result, we will select the correct label in most cases. So this is the approach. So basically, in ensemble model or fusion model, we are trying to combine models with different characteristics such that the correct prediction has higher confidence, incorrect prediction has lower confidence. And when we combine these two models, we will select the model with the prediction with higher confidence so that the combined model will have better performance than the individual models. So this is the idea. And here we have the action bank representation. We are using different seed values to generate different models. So the performance of a CNN depends upon the initial weights. We are using different seed value to initialize different CNNs so that we achieve different CNN models. So in addition, since this action bank representation is a grayscale image, I'm going to consider complementary action bank. Basically, it is negative of the action bank image, and I'm going to train the CNN on the complementary action bank. So as a result, I came up with, so if you see 0 to n, so n plus 1 models into 2, since I'm using complementary. So these output values, the confidence values, the predictions, we are going to take the maximum confidence across individual class, and whichever class has the highest confidence among these various values, we will assign the input to that corresponding class P. Okay. So this is how we have designed this fusion model, and as I mentioned, the ideal conditions for designing an efficient fusion model is we need diversity of the models as well as confidence value of correct prediction should be high, incorrect prediction should be low. So now we are going to design this approach and see whether these two conditions are satisfied or not. So the first condition being the confidence value of correct prediction should be high, incorrect prediction should be low. So to verify that, what we have done is for each of the model, okay, so this is 5-fold cross validation on UCF 50. So we will end up with 5 sets, and in each set, so this is trained on action bank and this is the trained on complementary action. So I'll find the average value, confidence value of the correct prediction, average confidence value of incorrect prediction. You can see that the average confidence value of correct prediction is almost 1, incorrect prediction is almost 0. That is the case for all the sets, indicating that we are able to satisfy the first condition. Now the second condition, the diversity of the models. To verify that, what we have done is we have taken an image representation and we have taken this matrix form. So each circle will represent the output of the corresponding observation. So this circle will be in red color if it is correctly predicted, black color if it is incorrectly predicted, and diameter of the circle will be proportional to the confidence value. So here there are P observations and the remaining will be marked as X. So here if you see, this is the CNN model trained on action bank with seed value 0. So in this representation, you see some gaps. Okay, so actually these are not gaps. Those are misclassifications. Those are small black circles. These are very small because in your previous slide, you saw that the confidence value associated with incorrect prediction is close to 0. So that is why you are not able to see these black circles, but these gaps corresponds to misclassification of this corresponding observation. So here, when you see these two images, you can see that for seed value 0, for example, in this particular case, you can see that more observations are incorrectly predicted compared to here. So when you combine these two models, you consider the same index, and whichever has the bigger circle, you will take it. So unless it is misclassified by both the models, it won't be misclassified in the fusion model. So here, as you can see, as a result, okay, when you combine these performance of these two models, this is the union of this model trained on action bank and complementary action bank. You are able to see, okay, less misclassifications compared to the individual models. So we repeat this process across the individual models, okay, and vertically across different seed values. As a result, you can see that unless there is a misclassification with high confidence value, all the models, all the observations are correctly classified. So if there is a misclassification with high confidence, that will be selected. So we will get the misclassification. So this is the numerical interpretation. So 130 are misclassified, 202 are misclassified. But when I combine, only 95 are misclassified. You can see for the rest also. And vertically, when I combine them, the misclassification decreases. So on UCF 50 data set, which has around 6,600 observations, only 21 are misclassified. As a result, there is an accuracy of around 99.68%. So here the performance is obtained by using a lot of models in Fusion, and the average performance of individual models is around 96 only. So that motivated us to see if there is a better way to initialize these models. So which led us to the development of the next approach, which is use of genetic algorithms to train a convolution neural. So these are some of the observations in this template videos. So this is the action bank representation, the videos in the action bank. So given a new video, we are going to compare that video with these observations to find the similarity. So the same approach as before, action bank representation, the same architecture. So here also we are going to consider the same architecture for this action bank representation. So in back propagation algorithm, so this is the global minimum. So depending upon where we start, time it takes to reach the global optima will vary. Okay, so this is in case there is only one, there is no local minima, then this is straightforward. But in case if we consider a complex error surface where there are local minima, so then it will be difficult to find the global minimum, or the solution might get stuck in a local minimum. So to address this, what we need is an approach to identify the various error basins and an approach to find the minimum within the error basins, okay, and a mechanism for these various explorations to communicate between each other. So here we need to identify different regions of error surfaces and find the local minimum and communicate so that we can find the global optimum solution. So here to use GA for optimizing a CNN, what we have done is for modeling the CNN, the convolution filters act as the feature detector. So that's why we have captured these in the GA chromosome, as well as the seed value used to initialize the fully connected neural network. So this is considered as a GA chromosome, and the classification performance is considered as a fitness value. So this is the entire approach. So what we do is we consider an initial population, let's say 20, and we do the fitness evaluation, selection, crossover mutation. And just before we do the fitness evaluation again, we use backpropagation to train the model. So basically, so this is the, so these are the GA steps, and this is the backpropagation step. So using GA, I find the initial weights, and once those initial weights are identified, I'm going to design the CNN, then train it with backpropagation algorithm for 50 pokes, then use the classification performance as the fitness value. So as a result, what happens is, for example, on the right hand side, if these three red circles indicate the various areas identified by the GA, and these white circles indicate the backpropagation algorithm, direction in which the solution will be explored. So in the next generation, it is likely to explore in this region closer to the global optima. And in the next generation, it will converge to the global optimum solution. So as a result, across generations, so the average fitness value will increase using genetic algorithm. So to analyze the impact of these various components, what we have done is we have checked the performance using the default neural network classifier. We are able to get around 96.8%. But instead of using a neural network, if we use an ELN classifier, we are able to achieve better performance. The reason could be that in this proposed approach, in the GA chromosome, only the seed value used to initialize the neural network classifier is optimized. As a result, it was not so effective in optimizing the neural network classifier. That's why instead of a neural network, if we use a ELN classifier, we are able to get better results. Then the training algorithm. So here we have used a population size of 20. Number of GA generations is 5. And BPA training is for 50 pokes. Number of generations is 5 and training is for 50 pokes. So here the CNN, if I train it for 5 generations, then I'm able to get accuracy only in single digit. But if I use BPA backpropagation algorithm only, train it for 50 pokes, some of the solutions might get stuck in the local minima. But if I use the proposed approach where I'm using GA and BPA, I'm able to get better results. So when I use various fusion rules, as you can see, irrespective of the fusion rule, I'm getting the same performance. So only one observation was misclassified among all the observations, thereby getting an accuracy of 99.98. And if I consider this top 2 performance, I'm able to get 100% accuracy. So to analyze, okay, how this GA, as the GA generations increases, how the solution is improving, what we have done is we have used, let's say, these values corresponds to the training and testing error when GA is used to initialize the weights. So after the weight initializations, we are training this CNN approach for key epochs. As a result, the training and testing error will reduce. So if I plot this initial training and testing error after GA initialization on the left hand side, and this error after training on the right hand side, and when I do this for all the candidate solutions explored during GA, so here on the left hand side, you see the performance of the solution obtained using GA initialization. On the right hand side, after training with backpropagation, you will see the performance. So what's happening here is training error, testing error. Okay. So this point, this circle color indicates in what stage of GA. Okay, right now it is at 20%, so it is around light blue. Okay, so here you can see light blue circle, and this middle one is the performance after backpropagation algorithm for 50 blocks. And on the right hand side, the same circle after training, okay, the corresponding error will be plotted here. So here, as you can see, as the GA generations increases, there are some solutions being explored which have lower error. So as the process is repeated, you will explore more solutions. Right now I am at around 45%, so 45 around greenish color. So you can see that I am finding solutions in the lower error region. And one more observation is all these solutions are lying on this 45 degrees line. The reason could be due to the use of n-fold cross-validation. The patterns in the training and testing observations are similar. Due to which the training and testing errors is the same. That is why these points are lying on the 45 degrees line. Right now at around 75%. So here you can see the yellowish circles. You can see that majority of the solutions are getting explored in the lower error regions. All the yellow circles you can see. So this is how we are able to verify that as GA generations increases, the performance of the candidate solutions explode, the performance is increased. As a result, you can we have seen it in previous slide also. Irrespective of which fusion rule we use, we are able to get good performance. The reason being that all the models are equally efficient or highly efficient. Now, coming to the last study where we use multimodal information for recognizing the human actions. So here we see a video in the both color and the depth information. So here the color information have finer details and the depth information is insensitive to lighting conditions. As a result, these two modalities have complementary characteristics. On the right hand side, you can see how this depth cameras work. So basically they have a emitter, and based upon the distance of various subjects, their reflectance will vary. The time taken for the reflected light to reach the sensor will vary, based on which we will generate this representation of this surroundings. So here we will use this temporal template representation. So the traditional temporal template representation for this particular case of one subject approaching the second subject. So these are the various frames across time. So in the traditional motion history image computation, the formulation is you binarize the image, and as you add new frames, you reduce the intensity value of the older frames. As new frames are added, the older frames will have the least intensity, recent ones will have higher intensity. And when you combine them using the max rule, you will end up with this representation of the action. So this is the traditional recursive computation of motion history image. So the same can be computed using this weight function, where I am directly assigning the weight values for these corresponding frames. And when I use the maximum of these computed frames, I will be able to get the same representation as the motion history image. So now from this curve, you can see that the older frames are given least weightage and the recent frames are given highest weightage. So we explored other possibilities. Is there a case where giving higher weightage to the beginning of the observation to the middle of the observation will give better results, or the same weightage for the motion across the observation. So we have explored all these possibilities, and as a result, we studied for these various actions. So here, this is for an interactions data set, and these are the outputs for these various temporal templates. Here you can see that, so the last column corresponds to the case where we are giving weightage to the middle of the observation. So here you can see for these particular cases where, okay, they are hugging or somebody is trying to hit another person, we are able to get better representation. And for other cases also, for example, one person observing approaching another person, the beginning or ending, there could be better representation compared to the middle. So like that, for different actions, different temporal template might be better. So that's why we have evaluated all possible temporal templates. So since this is a multimodal information, so given the depth information, I am going to compute the foreground and use it for computing the motion history image. Similarly, for the color information, I compute the frame difference, and from that I compute the motion history images. So both these motion history images are given as input to CNN for feature extraction, and these output coordinate features are combined by the classifier for recognition. So we have conducted this data study on SBU connect interactions, where these are some of the observations. So here what we observed is that when we are considering this mu3, so this is the depth and this is the color. So when we combine these two modalities, we are able to get better discrimination. And this is for only a single template. When we use combination of the templates, we are able to improve the performance further. And here, when we compare this approach with other approaches, so the other approaches are using skeletal features and we are directly using the raw video. So we are comparable with existing approaches. And on the bottom right hand side, you see the confusion matrix. So we have done the TSNE visualization of the features also. So here, in each of these plots, the same color indicates the dots corresponding to the same color indicates the observations for that particular class. So here you can see that there are few violets together. There are few yellows together. But there aren't many such clusters. Okay, if there are more of these clusters, that it means that we are able to get much better discrimination. So here on the right hand side, if you see, we are able to get much better clusters compared to these individual modalities. So we can conclude that when we use multimodal information, we are able to get much better discrimination. So it is also, experiments were also conducted on NATOPS dataset. So these are the various actions, and for some of these actions we need the hand gestures. And since we are not using the hand gestures, what we are going to do is I'm going to consider the top two. So here, depth and color, when we combine them, we are able to get better results. And when we consider the combination of these templates, we are able to improve the performance further. And as I mentioned, since I'm not using hand gesture information, I'm considering the top two analysis. So this is the comparison of the proposed approach with existing approaches. And here, as we are not using hand gesture information, I'm using the top two. And this is comparable with the existing approaches. Now, finally, on the media actions dataset. So here, also when we combined different modalities, we are able to see an improvement in performance. So here, the observation is that the color is around 40, but the depth is 90. So the reason is that if you see the actions, so actions like sleeping and stopping, okay, and something like sitting. So some of these actions, they does not involve motion. When there is no motion, when we compute the frame difference, it will be 0. If there is no frame difference, when we compute the temporal template, it will be empty. So that could be the reason why the color information, the performance is low compared to the depth information. So here also, when we combine different temporal templates, we are able to improve the performance. And when we compare the performance of the existing approach with the proposed approach, we are able to get better results than the existing approach. So with this, I conclude my presentation. To summarize, so we have discussed how deep learning models are different from traditional machine learning models. Then we have discussed about convolution neural network, its coordinate feature characteristics, and how the CNN design principles are used to design a CNN architecture and some of the applications. Then we have seen the stacked autoencoder, the various steps, and we have seen MATLAB demo. Then we have seen the visual analytics, the basic terminology, the definition of action recognition, what are the types, what are the modalities, what are the challenges. Then we have discussed the various case studies. So the first case study is how to use motion capture information to recognize human actions. So in that, what we have done is we have used domain knowledge to identify some of these markers that we want to use for computing the distances. These distances were passed through these fuzzy membership functions, which are like transfer functions to emphasize the discriminative information. These outputs are combined together to represent an image, to form an image, and that image is given as input to deep learning models like CNN and stacked autoencoder for recognizing human actions. The next approach is how to design an ensemble model for human action recognition. So in that, we have considered the action map representation of videos. In the action map representation, for different actions, the row associated with the higher similarity will vary. So that is why if we design a CNN architecture which retain that row information, we will be able to recognize them actions effectively. So that's why we have designed a CNN architecture using linear filters. Then to design an effective ensemble model, we need two principles. So basically we need the base models to have complementary characteristics, and the performance, the confidence value of correct prediction should be high and incorrect prediction should be low. So those are the two prerequisites for designing an efficient model. So we have designed this ensemble model by considering different seed values as well as using complementary action bank representation also to train the models. So once this experimental study is done, we have verified whether these two characteristics are met or not. So when we computed the average value of confidence value of correct prediction, it is close to 1, incorrect prediction, it is close to 0. And when we have used the image representation, a matrix-like representation, to see the observations correctly classified by the individual models, we are able to notice that when we combine different models, we are able to get better performance because of the complementary characteristics. So as a result, we are able to achieve a good performance, but we achieved it by using a large number of models, and the performance of the individual model is not so high. So that led us to investigating whether there is a better approach to initialize the weights of a CNN. So that led us to the use of genetic algorithms to design an approach for initializing the weights of a CNN. So here in genetic algorithm, we use a population, and using that population, the GS cycle phases, we generate a new population. And before computing the fitness value of the population, we use backpropagation algorithm for small number of epochs. so that it doesn't overfit. We train it, then the trained performance, we will use it as a fitness value. And we repeat this process for multiple generations, for 5 generations.
Hello. Hello, sir.
Hello, sir. Paul, sir. Hello.
Maybe some network issue. Dear participants, those who want to ask any questions regarding the topic, please post your message in the chat box. Dear participants, if you have any questions, please post the message in chat box. Sir is going to join in 2 minutes. Feedback will be shared in the chat box. Dear participants, please hold a second. Our resource person is going to join. If you have any questions, please post the message in the chat box.
Any questions?
Dear participants, Sir is available. If you have any questions, please post a message and you can interact with the resource person.
Dear participants, I enabled mic of all the attendees. We can directly ask the question. If you have any doubt or any queries, you can directly ask. Maybe, sir, I think there are no queries that participants are. You can continue.
So this majority of my presentation is based on my research work. You can find my publications from my Google Scholar. And I thank the organizers for this opportunity and the participants for patiently listening. Thank you.
Thank you, sir. It's a very wonderful session one can go through and for their research. So maybe participants who are working over this area can enjoy this work, enjoy this presentation, and they can work further based upon the content that you have provided to us. So thank you very much, sir.
Thank you. Thank you.
Thank you.
Thank you very much, sir.
Thank you.
Dear participants, please fill the feedback form so that we can end the meeting. Link of feedback form is provided in the chat box.